Here is a quartic. X to the fourth minus 6x cubed plus 12x squared minus 10x plus 3. The letters are real numbers throughout this episode. X runs over all of the reals. Nothing is restricted to integers. Nothing is complex. Your task is to draw it. Not sketch the general shape, draw it, with the turning points in the right places and the crossings at the right values. Most people answer that by differentiating, and differentiating is indeed where we will start. But before we do, it is worth asking a question that sounds almost rude. What does the derivative actually tell you? Because the honest answer is, much less than you think. So here is the thesis of this episode, and it runs against how calculus is usually taught. Differentiation is not a tool for drawing graphs. It is a tool for one specific question. Where does the function rise and where does it fall? That is nearly all it knows. Drawing a graph needs 3 separate pieces of information, and they come from 3 separate investigations. Where it crosses the x-axis, solve f of x equals 0. Where it crosses the y-axis, compute f of 0. Where it rises and falls, look at the sign of the derivative. 3 jobs, 3 methods. Nobody does all 3. The derivative does exactly one of them, and then it stops. Keep that division of labor in mind. We will watch it 4 times. Back to the quartic. Differentiate. 4x cubed minus 18x squared plus 24x minus 10. Now, a cubic derivative is not obviously helpful unless it factors, and this one does. Notice that x equals 1 makes it vanish. 4 minus 18 plus 24 minus 10 is 0. So x minus 1 divides it. Divide and the quotient factors again, giving 2 times x minus 1 squared times 2x minus 5. Expand that back and the coefficients return exactly. 4 minus 18, 24 minus 10. It is the same polynomial, so this is not an approximation or a guess. It is the derivative rewritten. And rewritten, it hands us its sign for free. Read the sign. The factor x minus 1 is squared, so it is never negative and it never changes sign. All the sign information sits in 2x minus 5. Below 5 halves the derivative is negative, above it positive. So the function falls, then rises, with its only turning point at x equals 5 halves. Something worth pausing on. X equals 1 is a root of the derivative, but not a turning point. The curve flattens there. The tangent is horizontal and then carries on downward. A flat spot is not a maximum, and this is where reading the algebra beats memorizing a rule. The minimum value itself is exact. Substitute 5 halves and you get minus 27 over 16. Not a decimal, a fraction. Now the second job, which the derivative cannot help with at all. Where does the curve meet the x-axis? Here we get lucky, and the luck is worth noticing. We already know that x equals 1 is special. Try it in the original function. 1 minus 6 plus 12 minus 10 plus 3 is 0. So x minus 1 divides f. Divide and keep dividing, and what comes out is x minus 1 cubed times x minus 3. Multiply that back out and every coefficient matches. 1 minus 6, 12 minus 10, 3. So it is an identity, not a numerical coincidence. The crossings are therefore at x equals 1 and x equals 3. A triple root at 1, a simple root at 3. Now put the 3 investigations together and watch the graph appear. From the derivative, falling, then rising, turning once at 5 halves, bottom at minus 27 sixteenths. From the factorization, it touches 0 at x equals 1 and crosses at x equals 3. From f of 0, it starts at 3 on the y-axis. And the triple root at 1 has a shape all its own. A simple root crosses straight through. A double root bounces off. A triple root does something stranger. It flattens onto the axis, kisses it, and continues through tangent to the axis at the moment of crossing. That is why the curve looks pinned near x equals 1. 3 pieces of information. 1 picture. No single method gave it. Second problem. An inequality, and a way of looking at letters that changes everything. Let b, c, and d be positive real numbers, and let x be positive too. 2 claims to prove. First, x cubed plus b cubed plus c cubed is at least 3 times bcx. Second, x to the 4th plus b to the 4th plus c to the 4th plus d to the 4th is at least 4bcdx. You may recognize these. They are the arithmetic geometric mean inequality for 3 and for 4 numbers. The instruction, though, is unusual. Prove them with calculus. That instruction is the interesting part, because an inequality between 4 symmetric letters does not look like a job for a derivative at all. The trick is in how you read the letters. Here is the move. Take the difference of the 2 sides and call it a function, but a function of x alone. Treat b and c as constants. They are letters, yes, but nothing says a letter has to vary. Fix them, and what remains is an ordinary cubic in one variable. X cubed minus 3bcx plus b cubed plus c cubed. Now the whole apparatus applies. Differentiate 3x squared minus 3bc. That is 0 when x squared equals bc. So for positive x, at x equals the square root of bc. Below it the derivative is negative, above it positive. One minimum, and its position is exact. Show that minimum is not negative, and the inequality is proved for every positive x at once. So evaluate it there. Substituting the square root of bc gives b cubed plus c cubed, minus 2bc times the square root of bc. And that expression is a perfect square in disguise. Write b cubed as b root b, all squared, and c cubed as c root c, all squared. Then the whole thing is b root b minus c root c, squared. A square of a real number cannot be negative. So the minimum is at least 0, and the inequality holds. Equality needs 2 things at once. X sitting exactly at the square root of bc, and b root b equal to c root c, which forces b equal to c. Put those together, and equality happens exactly when x, b, and c are all the same number. Not approximately, exactly. The 4-letter version goes the same way, 1 dimension up. Treat b, c, and d as constants and look at x to the 4th, minus 4bcdx, plus the other 3/4 powers. Differentiate 4x cubed minus 4bcd, which vanishes at the cube root of bcd. Again 1 minimum, again exactly located. Substitute, and what comes out is b times the cube root of b, cubed, plus the same for c, plus the same for d, minus 3 times the product of those 3 quantities. Look at the shape of that. It is precisely the first inequality again, applied to 3 new positive numbers. The 4-variable case is not a new proof. It is the 3-variable case, wearing different letters. Equality, for the same reason, needs all 4 numbers equal. Third problem. Count the solutions, then draw the answer in a different plane entirely. Let a and b be real numbers and consider x to the fourth minus a squared x squared plus bx. The question, for which pairs a, b, does this have exactly three distinct real solutions? And then draw that set of pairs in the B-plane. Notice what changed. The unknown is no longer a number. It is a pair of parameters, and the answer is not a value but a region, or, as we will see, a pair of curves. Before touching a derivative, do the cheap thing, factor. Every term has an x, so the expression is x times the quantity x cubed minus a squared x plus b. So x equals 0 is always a solution for every a and every b. One of the three is free. That leaves the cubic in brackets. Call it g of x, and we need the total count of distinct solutions to be 3. Two ways that can happen. Either g has 0 as one of its roots, in which case 0 is shared, and we need g to contribute 2 more distinct roots. Or g does not vanish at 0, and g itself must supply exactly 2 distinct roots, meaning g has a repeated root and one other. Take the first case. G of 0 is simply b, so this case is b equals 0. Then g is x times x squared minus a squared, whose roots are 0 and plus or minus a. Distinct requires a not 0. So the first family of answers is b equals 0, a not 0. That is the whole b-axis, with the origin punched out. The second case is where calculus enters. We need the cubic g to have a repeated root, and a cubic has a repeated root exactly when it touches 0 at one of its own turning points. So differentiate 3x squared minus a squared. If a is 0, this is never negative. G is increasing everywhere and has a single root, not enough. So it is not 0, and the turning points sit at plus and minus a over root 3. Now demand that g vanish at one of them. Substituting a over root 3 gives b equals 2 root 3 over 9 times a cubed. The other turning point gives the same with a minus sign. Check it once exactly. At a equal to root 3, that formula gives b equal to 2. So here is the answer, drawn where it belongs in the B-plane, not the XY plane. Two curves mirror images of each other. B equals plus or minus 2 root 3 over 9 times a cubed. Both pass through the origin, both are increasing, and both are steeper than they look near 0 because a cubed flattens there. Plus the horizontal axis, b equals 0. And the origin itself is excluded from all of it, because a equals 0 was ruled out at the start. That is the shape of the answer. A question about how many solutions an equation has, translated into a picture of 2 cubic curves and a line in a plane made of parameters. The argument above is the proof. The conditions were derived, not guessed. What follows is only a check that we did the algebra correctly. Take points on the curves. A equal to 0.7, 1.5, root 3, 3. And for each one solve the quartic numerically and count how many distinct real roots come back. Every case 3. Take points on the b equals 0 axis, 3 again. Then step off the curves deliberately, by 5/100ths and by 3/10ths, and count again. Not one of those gives 3. That is consistent with the derivation on the points we tried. It does not extend it. The reason the answer is correct is the derivative and the repeated root, not this table. Fourth problem, and the most general. Degree n for every n at once. Let n be an integer, 2 or larger, and consider this equation. X to the n minus x to the n minus 1, minus x to the n minus 2, and so on down through minus x, minus 1 equals 0. one leading term, and then every lower power subtracted. 3 things to show. First, that every turning point of f in the positive region has a negative value. Second, that there is exactly one positive solution. Third, that it lies strictly between 1 and 2. Note we are told we may assume f is positive for large X, which is obvious but tedious to prove, so it is handed to us. And notice, n is not a specific number. Whatever we do has to work for all of them simultaneously. First claim, the turning points are all below the axis. We are not going to find them. For general n we cannot, and we do not need to. Suppose alpha is a positive turning point, so f prime of alpha is 0. Write out f prime. N alpha to the n minus 1 minus n minus 1 times alpha to the n minus 2, and so on. Multiply that equation by alpha over n and subtract it from f of alpha. Every power of alpha survives, but each coefficient comes out negative, minus 1 over n, minus 2 over n, and so on. Since alpha is positive, every term is negative. So f of alpha is negative. That is the whole argument, and it never once needed the value of alpha. Second claim, exactly one positive solution. Start at the left. F of 0 is minus 1, which is negative. Go far right. F is eventually positive. So somewhere between, the curve crosses the axis. That is the intermediate value theorem, and it gives us at least one crossing. Now suppose there were 2 or more. Between 2 crossings, the curve must turn around, and the turn must happen above the axis, a maximum with a positive value. But we just proved every positive turning point has a negative value. So a second crossing is impossible. Exactly 1. And note the shape of that argument. Existence from a theorem, uniqueness from the previous claim. Neither came from a picture. Third claim, the solution sits between 1 and 2. 2 substitutions settle it, and both are exact. At x equals 1, every power is 1, so f of 1 is 1 minus n minus 1 more times. That is 1 minus n, which is negative for every n at least 2. At x equals 2, the subtracted terms form a geometric sum. 1 plus 2 plus 4, up to 2 to the n minus 1, which is exactly 2 to the n minus 1. So f of 2 is 2 to the n, minus that which is 1. Positive and remarkably, positive by exactly 1 for every n. Negative at 1, positive at 2, only 1 crossing in between. Therefore the solution lies strictly between 1 and 2. There is a second route to the same conclusion, and it is prettier. For positive x, divide the whole equation by x to the n. The leading term becomes 1, and every subtracted term becomes a reciprocal power. So the equation says 1 equals 1 over x plus 1 over x squared, and so on, down to 1 over x to the n. Look at the right-hand side as a function of x. Every term shrinks as x grows, so the whole sum is strictly decreasing, which means it can equal 1 at most once. That is uniqueness, with no derivative at all. At x equals 1 the sum is n, which exceeds 1. At x equals 2 the sum is 1 minus 1 over 2 to the n, which is just under 1. So it passes through 1 somewhere between. Now look at the small cases, because something familiar is hiding here. For n equals 2, the equation is x squared minus x minus 1 equals 0. Its positive solution is 1 plus root 5 over 2, the golden ratio, 1.618, and so on. For n equals 3, the solution moves up to 1.839. For n equals 5, 1.966. For n equals 12, 1.9997. The reciprocal sum makes the limit transparent. As n grows, the sum gains more terms, so the crossing point must rise, and the geometric series sums to exactly 1 at x equal to 2. The solutions climb towards 2 and never reach it. The golden ratio is simply where this family starts. 4 problems, and the same lesson underneath all of them. In the first, the derivative gave the rise and fall and nothing else. The crossings came from factoring, and the picture came from assembling 3 separate results. In the second, the derivative worked only after we decided which letters were allowed to vary. In the third, it located a repeated root, and the answer then had to be drawn in a different plane. In the fourth, it never located anything at all. It only told us the sign of the turning values, which turned out to be enough. So, differentiation is not the method. It answers one question well. The skill being taught here is deciding what information you actually need, and then choosing the tool that supplies it. A quartic with a triple root at 1, and a minimum of -27/16. An inequality that yields to a derivative once you fix the right letters. A pair of cubic curves in a plane made of parameters. And an equation of degree n, whose positive solution starts at the golden ratio and climbs towards 2. None of these was solved by differentiating and hoping. Each one needed a decision, first about what was worth knowing. A derivative knows where things rise. It does not know where they land.